Okay, so this is our first proper lesson on all the work on space, which is a Year 13 topic. Hopefully you've all watched the documentary from yesterday, which was the Jim Al-Khalili one about the Big Bang and everything else. There's a second part to that which I'll also post. You may well have even found it on YouTube, which is more about the end of the universe. All that stuff is relevant to us. We'll go more into the Big Bang a little bit later on. So what we're going to look at in this lesson today is two things. Well, more than two things, but I've split them into two parts here. The whole point is the different objects in the universe. So all the different things we find in space. The most important thing for us in terms of what we need to know is stars. And we're going to have a quick look at kind of what a star is, which we probably all know, and we're going to go back over the life cycle of a star from GCSE very quickly, and then look in a little bit more detail about the kind of the early stages of a star. Later on we'll go into a bit more detail about what happens at different stages of a star's life, and that is new stuff from GCSE. There's more details, and there's a bit more on things like the neutron star. And then we're going to have a look at some other things we find in space. So these things I think we'll all be familiar with. So planets, dwarf planets like Pluto, asteroids, planetary satellites, things like the moon. But it could also be ones that we've made and put up there. So things like the space station would be one of these. Then comets, solar systems and galaxies. So I think we probably all know what those things are. We just need to make sure we all have a bit of a clearer definition in mind for each one of those. So if we're asked in an exam what is an asteroid, you could give a really kind of clear answer to that question rather than just kind of write all sorts. Hopefully also you've had a chance to get outside and have a look at some of the things you can see in the sky at the moment. It's been really clear at night. I mean, it gets dark quite late. It doesn't really get that dark, does it, at this time of year? Not like in the winter, but hopefully you've seen some stars. Maybe a few weeks ago you watched those SpaceX satellites go over, and you had a chance to see Cygnus and do a little bit of research into that star Cygnus X1, which has the black hole going around it. And that was, I think I mentioned it in the description from yesterday, that was the first actual direct evidence of a black hole that we saw. So black holes were predicted, but that particular star was our first direct evidence of the kind of behaviour and the existence of black holes. So what we see is that star isn't obviously a black hole, but it's a star going round a black hole. Okay, so first point here is a diagram which hopefully is quite familiar to you from GCSE. So this is the basic life cycle of a star. So stars are complicated things, and if you do a bit of reading around and watch various documentaries and everything else, you'll see there's other stages which can appear. But this is our kind of our general pattern. So stars start off in a big cloud of gas and dust. And when we say dust, we don't mean the kind of dust that you might have on the top of your TV at home. It's little particles of matter. The gas, we're talking about hydrogen. So nebula are enormous, great big clouds of hydrogen gas, mostly, and other elements. And out of those, I'll show you a picture of a nebula in a few minutes. I would skip, it's on the next slide, I would skip on, but I think then it stops the whole recording of this. So I'll have to talk you through it and then show you some of the pictures afterwards. So a star like the Sun, which is kind of fairly average, fairly small for a star, would start off in a cloud of gas and dust called a nebula, and over millions of years you'll start to get clumping of some of these particles of dust and particles of gas, and these clumps get larger and larger as their gravitational pull starts to bring in other particles close together. And as more and more of those dust and gas particles are stuck together, the whole thing gets denser. We call this a protostar. as it gets denser and more massive, it gets hotter and hotter because gravitational potential energy, is being converted into thermal. As this stuff gets squashed together, it gets hotter. It's a bit like kind of clapping your hands. The kinetic energy of your hands moving gets turned into heat. Only with this star formation, it's gravitational potential getting turned into heat. And once the star reaches a temperature which is reasonably high, we call it a protostar. So it's not actually a star yet because it's not actually doing nuclear fusion. It's not producing its own energy, but it is a clump of gas and dust which is getting hotter. And eventually, some protostars will get so hot that they start to stick hydrogen nuclei together, and that process is nuclear fusion. Remember, fusion, this is going back to GCSE, we've not done nuclear fusion or nuclear fission yet as part of the A-level, but fusion is when we stick light nuclei together to make heavy ones, releasing energy. So once that protostar starts to take the hydrogen and stick it together to make helium, that's when we say it becomes a star. And this is where you get to this stage. And a star which is taking hydrogen and sticking it together to make helium, we would call a main sequence star. And this is the stage the Sun is at the moment. The Sun is stable. When this happens for a star, the star becomes stable. And we say that happens because there's an outward push. If you think about what's going on in a star, it's a massive nuclear reaction. It's like a series of nuclear explosions. So there's lots of energy pushing outwards. There's a kind of a pressure pushing outwards. And so long as that outwards pressure, we call that radiation pressure, so the outwards kind of blast of the energy release is being balanced by gravity pulling everything back together, that star remains stable. So something like the Sun, a main sequence star, is stable because the outwards radiation pressure is being perfectly balanced by the gravitational pressure pushing back in. Eventually it will start to run out of hydrogen and start to fuse together helium. And when that happens, the radiation pressure goes up, it increases, so the star swells in size and becomes a red giant. And it's still stable there. It can still carry on burning like that for billions of years, but it's not. It is much bigger in volume. And then eventually that will lose stability and it will pop, not in a massive dramatic explosion, but an explosion nonetheless, and you're left with this cloud of gas and dust, which is all the remnants of the star. And in the middle there, that bright spot, that is the core of the star, which is still there. It's no longer doing fusion, but it's gradually cooling down, and we call that a white dwarf. And that will cool down through the colours, so it'll become red dwarf, brown dwarf, and then eventually a black dwarf where it's not giving out any light at all. I think that the universe, well, I don't think this, I kind of remember reading that the universe is not old enough to have any stars which have cooled down and gone through this process, then become a white dwarf, then cooled down enough to become a black dwarf yet. But that will happen in the future. If your star is bigger than the Sun, so much bigger than the Sun, typically we say more than 10 times bigger than the Sun, that's in terms of mass, from protostar it will go to a much larger star. So this is still main sequence, still fusing together hydrogen, just on a much bigger scale. And because it has more mass, it can balance out a greater outwards radiation pressure with its gravity, so it can fuse heavier and heavier things and become much larger while still being stable. Eventually though, that will become even more unstable than the situation up here for the planetary nebula, and explode in an enormous explosion called a supernova. And we do this in a lot more detail later on, so I won't say too much about this now. And after the supernova we have two options. The star can either become a neutron star or a black hole. So that was our kind of GCSE life cycle of a star. What we really need to be thinking about right now is what's happening here. So in a nebula, a cloud of gas and dust, that gas and dust can clump together forming a lump of matter. That lump of matter is called a protostar. That protostar will drag more and more stuff inwards and into it, and that will produce heat, gravitational potential energy will be converted into heat as that mass is compressed into that lump. Eventually that protostar can get so hot it can cause nuclear fusion to happen, and then you have a star, a main sequence star. Main sequence stars are stable because the outwards radiation pressure is being balanced by the inwards gravitational forces, the gravitational pressure. So just to give you a bit more of an example of this, I'm going to skip on. And this is an example of a nebula. This is the Orion Nebula. So you can see this, it's most obvious in the winter when you see the constellation Orion a bit more clearly. And the Orion Nebula looks to us like a blurry star about halfway down the sword of Orion. If you have binoculars or a telescope, you can see a little bit more of the kind of the blurriness of the cloudiness of it. You won't see it in these colours. These colours aren't kind of a true picture of what it looks like. This is a false colour image to show the presence of hydrogen, and I think the pinks in here are where there's more hydrogen present. But in this cloud, which is enormous, in this cloud you'll get protostars forming, and then maybe some of those protostars turning into main sequence stars fusing together hydrogen to make helium. So that's an example of a nebula. And if you go onto, say, Google Images and type in nebula, there's loads of really quite beautiful pictures of different nebula around that we have seen. Right, this is quite a simple diagram, just trying to summarise that idea of what it takes for a star to be stable. And main sequence stars are stable because the radiation pressure, which are the kind of the green and the blue arrows pushing outwards, that's the pressure outwards from that nuclear reaction. That pressure is being totally balanced by gravity pushing in. If the radiation pressure becomes too big, gravity is no longer strong enough to hold it in place, and the star will expand until eventually the gravity can start to balance it out again. So stars are a constant kind of balancing act between getting the radiation pressure and gravity exactly the same. Right, so that was the first kind of part, so stars and the life cycle. We are going to keep going back to that life cycle, but for now all I really want us to get from today is just a little bit of a recap of the GCC life cycle of stars and that early stage, so protostars to main sequence. Other objects in the solar system then. So here is a picture of our solar system. Ignore this click or touch an object to explore. I got this picture off a Google image search, not sure where it came from, and clearly this is not to scale. But what we're looking at here, first of all, is the planets. And planets are objects which are large enough, have enough mass to have a kind of a spherical shape, roughly. So, for example, the Earth isn't exactly spherical, it's a bit squashed, but it's kind of round. So the planets are round, they have their own shape, they're regular shapes. So in comparison to one of these asteroids, they're all kind of irregular and lumpy. So planets have to be roughly spherical, have to be big enough to be spherical. And that's important with our distinction between planets and dwarf planets. They can't be doing any fusion reactions, so they can't be kind of producing their own energy through fusion. And that's important. If an object is producing its own energy through fusion, it's a star. If it isn't, it's a planet. And another important distinction between planets and dwarf planets is it has to have cleared, so a planet has to have cleared its orbit of most objects. So if you've got an object which has loads of bits and pieces floating around it, and it's just kind of a sea of lumps of rock and everything else, then we wouldn't necessarily consider it to be a planet. The Earth is a planet because even though it has something going around it, the Moon, it's not got all the other kind of bits and bobs. Jupiter has an enormous number of moons, but they're in kind of a nice pattern. They're proper moons. Pluto, we would now describe as a dwarf planet because it doesn't have that same nice pattern. It hasn't cleared its orbit of all those other things. It's part of a large number of other similar sized bits of rock which are all kind of orbiting around each other. So it's not got its own kind of clear sort of space that it's cleared for itself. It's just a big collection of other rocks. And now we're finding more and more similar sized dwarf planets to Pluto out in this area of the solar system. So dwarf planets haven't cleared their orbits of sort of small objects. Asteroids then are objects which are in orbit around a star, but they're too small to be regular sized, and they're too kind of uneven. They're not spherical, they're lumpy and bumpy, and they're small. And they're similar to comets, only with comets contain ice, asteroids do not. So asteroids, small lumpy bumpy rocks that are too small to be considered a planet that are orbiting a star. Comets are balls of ice and dust and maybe small bits of rock that orbit a star in a highly elliptical orbit. So they're not going around in what looks to be circular orbits like the asteroids in this asteroid belt here between Mars and Jupiter. Comets go around in big kind of sweeping elongated orbits, big extreme kind of ellipses, I'm not sure if that's a word, big oval shapes. So at some points they go very close to the Sun, and other times they go much further away. And this whole collection of objects going around a star, so planets, asteroids, comets, dwarf planets, are all a solar system. So our solar system is the stuff going around the Sun and the Sun, but we think there are lots and lots of other solar systems out there, systems of planets going around a star. The other thing we haven't mentioned, which you can't really see in this picture because of the scale, is you have planetary satellites. So planetary satellites are the moons of the planets and artificial satellites we put up there. So if you think about the Earth, the planetary satellites around the Earth are objects going around the Earth, so they are the moon and all the wide variety of satellites and spacecraft we've got up there. Mercury and Venus don't have any planetary satellites. Mars has a couple of moons, which are really just kind of captured asteroids, but they are planetary satellites of Mars because they're going around Mars. Jupiter has lots of planetary satellites, lots of moons going around it. So planetary satellite is an object going around a planet. And then finally, so if we kind of zoomed out of this image, and I haven't got a zoomed out picture of this, we would get to galaxies. And galaxies are collections of stars, so large collections of stars which contain anywhere between billions to hundreds of billions of stars. Sometimes they appear in these big spiral shapes, other times they're more irregular. But galaxies are our largest objects which we can see as distinct objects in space. Right, if we can have a go at those questions, they should take you about 15 minutes or so, and then tomorrow I will put up the answers to these so you can mark them and see how well you've done.